So I'll open this talk with the following comment on the subject of thermodynamics. It says thermodynamics has something to say about everything, but does not tell us everything about anything. Okay, so this is one interesting comment, I find it. And the next statement is by none other than the Arnold Sommerfeld. He says thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you don't understand it. But by that time, so you are so used to it, it doesn't bother you anymore. So even people like Sommerfeld make such comment. Okay, so that's the kind of intricacies involved in the subject of thermodynamics. Right, as I told you, the story of thermodynamics is very, very long, starting from 1593, Galileo Galilei, who invented the first thermometer using water. And then, the list goes on, Benjamin Thomson, Avogadro, Fourier, and so many other people. And Sadi Carnot, you have a Mayer, Helmholtz, Joule, Clausius, Maxwell, and so many other people. Okay. So the central quantity here is actually the entropy. As far as the connection between thermodynamics and statistical mechanics is entropy, which was introduced by Rudolf Clausius in 1865, where he introduced the notion of second law of thermodynamics. Okay. So this is just a tapestry of this some important names which I mentioned. Yeah. So I hope you can recognize some people like Avogadro and Boltzmann and some people, Maxwell and so on. Okay. Right. So I will touch upon only the entropy, or rather I will discuss on the first and second law of thermodynamics as much as possible. At the end of the second law of thermodynamics, you should be in a position to appreciate entropy, so that you can that will give you the gateway to the domain of the world of statistical mechanics. Okay. Right. Let's start from some basics. Okay. So the secret of universe is lying when you think everything in terms of energy. Okay. When you say energy, it is broadly classified as mechanical and non-mechanical. Mechanical is what we call it as work done by you when you are pulling a chair, or work done by a gas when it expands, right? And so on. Non-mechanical is the energy which is through the supply of heat. When you heat an object, it acquires energy, right? So thermodynamics is a subject which deals with both the forms of energy. So this simple cartoon will help you to understand what you're talking about. So essentially, you're trying to understand a system which is going to interact with the environment. Okay, system is a very, very small subject. It's an object which is of small size, and environment is something which is everything other than the system. Okay. So the system will continuously interact with the environment. So that interaction makes things very complicated to study. Okay. And there is a boundary. Through this boundary, the system will interact with the environment. And then depends on the nature of the environment. Depends on the nature of the boundary. The interaction will be, classified into different ways. Right. So we'll classify the systems into three types based on how the system interacts with the environment. Okay. Our interest is only on the system and not on the environment. But the interaction of the environment and system is very important to understand the behavior of the system. So we can classify the systems into three types, depends on how they interact with the environment. So first one, we call it as the thermally isolated system, where the system does not exchange energy with the environment. Okay. And the second one is, we call it as a closed system, where the system exchanges energy with the environment. Okay. So here only energy is exchanged between the system and the environment. And the third one is the most complicated situation, which we call it as the open system, where the system will be exchanging energy and the matter particle with the environment. Okay, this is the most complicated situation and more realistic situation. So in order to understand this open system, which is our final objective, we will be starting from the notion of the simpler situation where system is thermally isolated. Okay, and then we go on to closed system, then we go on to open system. In fact, this is the three class of systems based on which we have the three ensembles which you learn in the subject of statistical mechanics. You introduce the notion of microcanonical ensemble to understand the first type. Then you go on to introduce the what is called the canonical ensemble to model the closed system. Then you go on to develop the subject to the level of grand canonical ensemble, which models the open system, right? Okay, let's start with some few definitions, then we'll move on systematically. So here we are going to talk about a system of n particles, right? So when I say n, it's of the order of 10 power 23 particles. The particles could be either atoms or molecules or ions. Okay. And of course, we are not really interested to see what these individual particles are doing. Thermodynamics is interested only in the bulk or macroscopic properties of a system. When I say macroscopic or bulk properties, they include quantities like pressure, volume, temperature, and so on. So from the thermodynamic perspective, these quantities are sometimes called as the thermodynamic variables. Later on, I will qualify why I call it as the thermodynamic variables. Okay, not every quantities can be called as the thermodynamic variables. It requires some mathematical qualification, which I will describe later on. So if you start with a simple system like gaseous system or fluids in general, so the convenient quantity we are interested is pressure, volume, and temperature. Now, intuitively, you think that there must be some relation between these quantities, right? Definitely, there must be a relation, but we may or may not know, or we may or may not be able to dig out the relation. But it is fairly correct to assume that there exists some relation among them. Okay, so this unknown relation between these quantities can be written down like this: some function of PVT is equal to 0. Such kind of equation is called as the equation of state. Something like this: P minus G square by T equal to 0, or something like that. Yeah. So the equation of state describes the state of a system very clearly. Okay, this is very, very important. Usually we do not know the equation of a state of a system. Probably we know the equation of state for some simple cases like ideal gas and so on, which I will come later on. So if that is the case, there exists a relation between P v T like this. If this is the case, one can always write P in terms of V comma T, or V in terms of P comma T, or T in terms of P comma V. So all are equivalent. Okay. If I write P as a function of V comma T, here what I assume is that V and T are independent variables and P is a dependent variable, right? Similarly, in this case, V is a dependent variable and T is the dependent variable in the third case, right? So with this description, one can represent the state of a system. Okay. So as I told you here, if you take any two variable as an independent variable, here let's say I take V comma T, then if I know the value of V and T, I can always find out P. So V and T are my independent variables. Similarly, I have others. Okay. If I take P and V as my independent variable, I can represent the state of a system by giving the value of P and value of V. Of course, they are measurable quantities, right? Then one can always find a relation of one can always find T in terms of P and V from the equation of state which you have. Okay. Right. So if I take P and V as my independent variables, I can draw what is called the PV diagram. In this diagram, the state of a system at some instant of time is being represented by a point, right? At some instant of time. Now, as time goes on, the state of a system will keep changing, right? it will go from one point to other point, right? So this is what we call it as a, so this point will trace a trajectory on this PV diagram. This is what we call it as a process or thermodynamic process. Okay. So we are always interested to find out the state of an equilibrium state. What do you mean by equilibrium? Equilibrium state is a state which does not vary with time. Let's say that there is an equilibrium state here. The system doesn't change. And we know that the system is going to interact with the environment. If it interacts with the environment, definitely something will, change will happen. So the change will happen such that it will form a trajectory over here. Eventually, after some time, it will reach to another equilibrium state, right? So essentially, the system will undergo a thermodynamic process from one equilibrium state to another equilibrium state. Okay. So we are always interested in the equilibrium states. Okay. In the absence of external disturbance or force, all systems continue to be in an equilibrium state. So the equilibrium also can be classified into mechanical, thermal, and chemical, which also I will come to it why there are three. Okay. So if the system maintains all the three equilibrium, we say that the system is in thermodynamic equilibrium. Okay. So you have to appreciate the notion of equilibrium state of a system. Right. Having defined the process, one can classify the process broadly into two types for the convenience of the investigation. Okay. If I is the initial state of a system, initial equilibrium state of a system, and F is the final equilibrium state of a system, then I said there is a process which takes the system from I to A. And this trajectory I call it as a process, right? If suppose I go from I to F on this path, and if I'm able to come from F to I on the same path, then such a process I call it as the reversible or ideal process. Reversible or ideal process. If I go from I to F along this path, and if I'm not able to come back along the same path in the reverse direction, then it is a one-way traffic. Okay. Such a process, we can call it as the irreversible or real process. Unfortunately, most of the process happening in nature are irreversible process. Okay, so you do not know the path for the system to go from I to F. We don't know this path in most of the natural process, almost all the processes. Okay, so this kind of processes are difficult to study. Okay, and this process are ideal, which are simple to study. Okay, so we should know how to handle these kind of processes. Okay. Right. If that is the case, since you don't know the path, you may be interested to understand only those quantities which does not depend on the path. If you have a quantities which depends only on the initial and final state, then life is relatively easy to handle, right? So we are looking for only those quantities which are independent of the path. That's a first and foremost. Okay. Right. And you also, in thermodynamics, you also come across what is called the cyclic process, where the system goes from state A to state B along the path 1, and from B to A along the path 2, right? So the initial and final states are same. So such a process is called as the reversible cyclic process. When I say reversible, you can go from A to B along the clockwise direction, and A to again A along the clockwise, and A to B to again A along the anti-clockwise. If you're able to go along the same direction, reverse it, and such a cyclic process is the reversible cyclic process. So cyclic process, reversible path I make it by a solid line, and irreversible process I make it by a dotted line. So one can also have this kind of process: A to 1' to B, and B to 2 to A. So this cyclic process is a irreversible cyclic process. Okay. So cyclic process, again, simple process by which one can make use of it for various applications. Okay. Right. So this is something very important. Okay. As I already told you, since we do not know the exact path for any process, we are interested in only those quantities which are independent of path. So how do we know that which quantities are independent of path? So in order to appreciate that, we have there is a beautiful notion called exact differential. I will go through this slide. Please follow it carefully. Once you understand the notion of exact differential, the remaining thing will be much easier. Okay. If suppose you have a function f of x, which is a single valued continuous and differentiable function, and you are interested to know how the infinitesimal change in x affects the change in f. Okay, the infinitesimal change in f, if you are able to write this df in terms of dx as follows, then this differential is called as this infinitesimal change in f is called as the exact differential. Okay, if you have a single valued function f of x, then df is equal to df by dx into dx, that you know. So this relation tells you the change in x affects the change in f in this way, right? If you are able to write like this, then df is called as the exact differential, which is possible if it is a single valued continuous and differentiable. Okay. If such is the case, the change in some function f of x moving from point x1 to x2, you just integrate this df from x1 to x2, which is equal to f of x2 minus f of x1. This is equal to this only because this is the case. So which I call it as the delta f. So delta f is the change in the function when you move from point x1 to point x2. So this change depends only on the value of the function at the endpoints, right? And this notion can be immediately extended to functions of more than one variable. As I told you earlier, we will be dealing with function of two variables, right? If you take p and v as an independent variable, t will be function of p and v, right? So we should know how to handle the function of two variables, right? Extending this notion to a function of x comma y, the infinitesimal change in f can be written as df equal to dou f by dou x dx plus dou f by dou y dy. Of course, when you differentiate f with respect to x, you keep y constant. And similarly, when you differentiate with respect to y, you keep x constant. So this is basically the partial derivative, right? So this is how the change in x and change in y affects the change in f, right? So this is a relation, right? If that is the case, when you go from point x1, y1 to x2, y2, you see what is the change in f. That change in f, one can write it as delta f, which is equal to integral df from point 1 to point 2. Point 1 represents x1, y1, and point 2 represents x2, y2. And this integration is exactly equal to this because we have this. Okay, of course, here also we assume that the function f is a single valued continuous and differentiable, right? If df is equal to this, then only integral df is equal to this, which is f of x2 comma y2 minus f of x1 comma y1, which I write it as f2 minus f1. f2 is the value of the function at x2, y2, and f1 is the value of the function at x1, y1. So the change in f depends on the value of the function at the endpoints, right? So in that sense, the change of f is independent of the path when you move from point 1 to point 2, right? When you take 2 points x1, y1 and x2, y2 in xy plane, you can go from point 1 to point 2 in infinite ways, right? And you see here that some function f of x comma y, that f, the change in f when you move from point 1 to point 2, it only depends on the value of the function at point 1 and point 2. It doesn't depend on which way you take from 1 to 2. Is it clear? Is it clear?
Yes, sir.
Okay. Okay, so this is what I'm mentioning 1 to 2, I go along this path, right? And I go along this path, I can go along this path, right? Doesn't matter whether I go by this path or this path. The change is always depending on the value at F2 and the values at F1, right? Okay. Right. Now, suppose, imagine that I'm going to consider a cyclic path. That means I go from 1 to 2 along this path, then 2 to 1 along this path. Okay. Right. For a cyclic path, what do? I have to compute the same thing for a cyclic path. Delta F is equal to integral. This is cyclic integration, right? The integration of df over a cyclic path. So this is my cycle 1 to 2 and 2 to 1. Okay. 1 to 2 and 2 to 1. So for a cyclic path, delta F is equal to integral df, which is nothing but df integration from 1 to 2 along this path plus integration df from 2 to 1 along this path. So because this quantity, as you know, it is F2 minus F1, and this quantity, as you know, it is F1 minus F2, right? So when you add up, it will be 0. So the change will be 0, right? So for a cyclic path, the change is 0 because it depends only on the endpoints. For a cyclic path, the initial and final states are same. So there is no change in the quantity. This is one way of understanding what we call the quantity which are independent of path. Okay. So for a quantity which is independent of path, the change will be 0 for a cyclic process. Okay. This also implies that you take a derivative of f with respect to x first, then you take a derivative with respect to y, which is exactly equal to take a derivative of y with respect to y first, then x. This implies this. Okay. So whether you go from here to here and here, or here to here and here, the change is going to be the same. That's what it means. Okay. The change in x first, the change in y is equal to change in y first, then change in x. Okay, so this is a very important relation. And this relation is what we are going to use it later on to derive various relations from the Maxwell's various relations from the Maxwell's equations. Okay. Is it fine so far?
Yes, sir. Hello.
Okay. Yes, please.
Sir, fine. Are you asking anything? Fine, sir.
Okay, okay, yeah. Thank you, thank you.
Okay.
So of course, as I mentioned earlier, there are two forms of energy. One is called the mechanical energy, or we call it as the work. So that's what happens, when you fill a cylinder with the gas and you push or pull the piston, the gas will compress or expand. Essentially, the gas is doing a work, right? So I call W or delta W is an infinitesimal work done by the gas. Okay, when you have a gas filled in the cylinder, when the gas expands, so this expansion of gas essentially is happening because the gas is actually doing some work on the piston to move up. If it is pushing the piston up, and so that there is an infinitesimal change in the volume dV, then under the pressure P, then the work done by the gas is delta W is PdV. Okay, that you already know. So if you know this delta W for a small change in volume, you just integrate this from some initial state to final state, and so that you will find the total work done by the gas. Okay. Usually in mechanics, we talk about work done on the system. Okay. And here we have a convention of work done by the system. Okay. So there is a change in the sign when you go from mechanical, the convention used in mechanics and the convention used in the thermodynamics. Of course, in some book they use the other way also. If that is the case, you have to be careful with the sign. Okay. Here W I call it as the work done by the gas. Okay. So W is equal to integral VI, VF, PdV, where VA and VF are the initial and final volumes. So essentially this W is nothing but the area under the curve from I to F. If this is the initial state and F is the final state of the gas inside the cylinder, the area under the curve is the work done by the gas. So as you see here, W is the area under the curve, and obviously W is a path dependent quantity. W is a path dependent quantity. Okay. Right. If suppose the process goes in some other direction, W will be different, right? It's a path dependent quantity, which you have to keep it in mind. Okay. On the other hand, we have a non-mechanical energy or heat. Sometimes it is called as the non-mechanical energy in transit. Okay. This is the mechanical energy in transit is work, and non-mechanical energy in transit we call it as the heat. If suppose you supply a small amount of heat to a system, we say that there is a heat absorbed by the system of mass m. So that infinitesimal heat supplied or absorbed by the system, supplied to the system or absorbed by the system, is represented by delta Q, which is intuitively we can say that this is directly proportional to the mass of the substance or system and change in the temperature, right? Delta Q is proportional to m dt. So here you can notice that as you see here I put dt, here I put delta Q. Similarly, here I put dV, here I put delta W. It will be clear why I'm putting this distinction. Okay. So if that is the case, the total heat absorbed by the system when it goes from some initial state I to final state F, you just integrate this quantity from I to F, which is the total heat absorbed by the system in a process. Again, this is also a path dependent quantity. Okay, this is also a path dependent quantity. Okay, so if W is a path dependent quantity and Q is also a path dependent quantity, then the differential delta W and delta Q both are not exact differential in the sense which I mentioned earlier. Right, delta W and delta Q, they are not exact differentials. And so W and Q upon integration will give you a quantity and both are path dependent. Okay. This is something which you have to keep it in mind always. Yeah. So if Q1 is the heat absorbed by the system and if Q2 is the heat released by the system in a process, the net heat absorbed is Q1 minus Q2. As I told you earlier, you have to take care of the convention. Heat absorbed I call it as Q and heat released I call it as minus Q. So total heat in this process is Q1 minus Q2. Okay. So if you take the unit mass m equal to 1, one can also define a quantity called specific heat capacity, which is delta Q by delta T, which is the Q cannot be measured. Okay, it's difficult to measure, but delta Q by delta T can be measured, and this quantity is sometimes called as the heat capacity. Heat capacity is a very, very important quantity in the thermodynamics because it is a very, very important quantity which can be measured in your laboratory. Okay, right. So here I've been talking about a gaseous system where P and V are my independent variables, right? Of course, you can think of any kind of system, electrical system or magnetic system or any kind of system. Accordingly, the delta W will change. Okay. So here I'm assuming that the system is a gaseous system. So I have PdV. Okay. So it depends on the system, the work done by the system will be changing as given over here. Work done in different systems. Okay, so you have a fluid, you have a pressure and volume. The work done is PdV. So this is sometimes called as the intensive variable, and this is called as the extensive variable, as you know, right? If you have a stretched wire, so P will be replaced by F and V will be replaced by L. And surface for a film, if you take a surface of a film, you have a surface tension sigma play the role of P and the area of the surface play the role of V. Similarly, electrochemical cell, the EMF play the role of P and charge Q will play the role of V. Dielectric slab, it is electric field E and P, and for the paramagnetic rod, the magnetic field H will play the role of P and the magnetization M will play the role of P. And accordingly, the work done is given over here. Of course, here it is positive, here are given negative because of the sign convention which you have to appreciate. Because when you talk about the paramagnetic rod, you apply a magnetic field M. So H dm is the work done by the magnetic field, and minus H dm is the work done by the magnetic system, which is of your interest. So I hope the sign convention should not be you should be very careful with the sign convention. Whether we are associating W to the work done by the system or work done by the external force. Okay. Okay. So with this idea of heat and the work, one can understand the what you call the first law of thermodynamics. Somnath, when should I complete? Hello?
Yes, sir. I can hear you, sir.
When should I complete? 1 o'clock, right?
The session is from 11 to
11:30.
1.
Sir,
11:30.
you have time till 1. 1
Okay,
o'clock.
fine. Okay,
Sir.
sure. Thank you. 11:30 to 1.
11:30 to 1. Yeah.
Okay, yeah. So the heat absorbed is a gain of energy, right? And work done is a loss of energy, right? You're spending time, you're spending energy, right? So work done is a loss of energy and heat absorbed is a gain of energy. And as I mentioned earlier, both are path dependent. So now you define a quantity called change in energy. The change in energy, I call it as delta U, which is Q minus W, right? So this is basically a statement of conservation of energy. Delta U is equal to Q minus W. It is interesting to note that delta Q, delta W, they are not exact differential, or they are not perfect differential. Okay. But delta Q minus delta W, I denote it as du. Interestingly, you see that du is an exact differential, and so this u is independent of path. Okay, and this quantity is called as the internal energy. This internal energy is also understood as the sum of energy of all the constituent particles. So essentially, the first law of thermodynamics gives you a quantity called internal energy, which is a thermodynamic variable in that sense. I mentioned to you earlier, right? Thermodynamic variable is a variable which is actually a quantity which is independent of path. Okay, the change in that quantity, it depends only on the endpoints. Or in other words, the differential of that quantity is an exact differential. Okay, so I have a d here, I have a delta here. So this you have to differentiate. So du is an exact differential. Of course, one can prove that du is an exact differential and delta u is a path independent quantity, but I'm not going to spend time on it. In fact, it's a little bit of mathematics, but I will just skip it. Okay, I will only justify it pictorially. Suppose you have a system from point A to point B. I can think of infinite number of ways from point A to point B, right? So the change in the internal energy of a system when it goes from A to B, which is delta U, which is integral A to B du, since the du is an exact differential, the change delta U is just UB minus UA. What is UA? UA is the energy of the system at state A and UB is the energy of the system at state B. So the change is just UB minus UA, right? So the change of U is independent of the path or the process. It depends only on the initial state A and the final state B of the system, right? So in that sense, U is qualified to be a thermodynamic variable. Okay, any question at this point? Okay, if not, I assume that you're following me without any difficulty. Okay, so here I'm proving why it is exact differential. I'm not going to the detail of it. Okay, then there is a notion called specific capacity. Okay, and one can also write down this. By the way, this is the statement of the first law, right? Either you can write this as a first law or you can write this as the first law. First law written in terms of infinitesimal change in Q. Okay, du is equal to delta Q minus delta W. That is the first law. Right. I will not go into the detail of all these specific capacity, which you already know. Right. Okay. As I mentioned to you earlier, most of the processes are very complicated to study, and so writing the equation of state is not so easy. But it is easy for certain ideal systems. So one such ideal system is called as the ideal gas. What do you mean by ideal gas? Ideal gas is a gas which has sufficient low pressure and sufficiently high temperature. If you think of a gas, whatever be the gas, hydrogen or nitrogen or oxygen or any gas you take, people have found out painstakingly from a series of experiments that all these gases at low temperature, low pressure and high temperature, they all behave in the same fashion. So what do you mean by same fashion? They behave in such a way that the pressure, volume, and temperature, they follow this equation. This is true as long as the pressure is low and temperature is sufficiently high. So this is what I mean the equation of state of an ideal gas. This is the ideal condition. Okay. And of course, N is the number of moles and R is the universal gas constant, and T is the temperature. And you should remember that T is the temperature measured in Kelvin. Okay, right. And Kb, of course, is R by Na, where Na is the Avogadro number and Kb is the Boltzmann constant. So you can also write the same equation as Pv equal to N Kbt, right? Or Pv equal to nRT. If you take 1 mole of a gas, it's Pv equal to RT, right? And one can show that for such a gas, since we know this equation of state, we always handle ideal gas for all our understanding, right? We keep referring to ideal gas to test all our understanding or to test all our hypotheses or whatever theory you develop. Okay. So for such an ideal gas, one can define heat capacity at constant pressure and constant volume, and the ratio of this constant pressure and constant volume, the ratio of the heat capacity at constant pressure and constant volume, which is sometimes called as the adiabatic index, which is exactly equal to 5/3. That's because of the fact that Cp minus Cv is exactly equal to R, which you already know. Okay. Then one can also think of some simple process where there is no change in pressure, which is called the isobaric process. No change in volume is isochoric process. No change in temperature is isothermal process. And no supply of heat is the adiabatic process, right? So that I have mentioned over here. A to B is the isobaric, where there is no change in pressure. This is B to C is the isochoric, and yeah, and you can also think of isothermal process and adiabatic process, right? So these processes are considered to be reversible process. So you can go forward and you can also go backward in the same direction. So one can also write down the gas equation which goes through this process. So if you take a isothermal process where PV equal to, if you have an ideal gas which undergoes an isothermal process, PV is equal to constant because T is constant, right? So PV is always constant for an ideal gas when it goes through the isothermal process, right? And if you think of an adiabatic process, the gas equation is PV power gamma equal to some constant, where gamma is the adiabatic index, which is Cp by Cv. Okay, right. So I'm recollecting all this because if you know these elementary things, you'll be able to solve some simple problems without difficulty. We are just recollecting what we already know. Okay. Now we come to the notion of the second law of thermodynamics. The second law of, see, the first law of thermodynamics introduced a quantity called internal energy. And we know that du is an exact differential. The second law actually concerns about the conversion of one form of energy to the other form of energy. For example, how do you convert the heat to work and so on, right? So the clause here, there are two fundamental statements about second law of thermodynamics, based on which one can understand how the conversion is, how we can convert the heat energy to mechanical energy effectively. So there is a model called Carnot cycle proposed by Sadiq Carnot in 1824. He proposed the idea of how to convert the heat to work continuously or repeatedly. So he constructed a cyclic process like A, B, C, D, A by constructing, a pair of isothermal process and pair of adiabatic process, right? So by executing such a cyclic process using a working substance, it is possible to convert heat to work continuously, right? If you supply a heat Q1 to the system, and if the Q2 is a heat rejected from the system, then the work done is actually W, which is Q1 minus Q2, right? And this is true because this Q is equal to W, because for this cyclic process, the change in energy is 0. That's why Q is equal to W. Q is Q1 minus Q2, which is W. And if you have such a engine is actually a device which converts Q to W continuously. Then one can define the efficiency as work output by heat input. Work output is Q1 minus Q2, and heat input is actually Q1, which is 1 minus Q2 by Q1. And one can show that Q2 minus Q1 is equal to T2 minus T1. This is a very, very important relation. Of course, this is true only if the working substance which undergoes this cyclic process must be an ideal gas. For such a process, Q2 by Q1 is exactly equal to T2 by T1, so that efficiency eta is just equal to 1 minus T2 by T1, where T1 is the temperature of the, what do you call, the temperature of the reservoir maintained at higher temperature, and T2 is the temperature of the reservoir maintained at the lower temperature. Whatever be the substance you use, if as long as it is an ideal gas, okay, this efficiency depends only on the temperature T1 and T2. Okay, that's because of the fact that Q2 minus Q1 equal to T2 minus T1, which is true only for the ideal gas. You will have, good, definitely people, there'll be a set of questions using these relations. I see that repeated questions appears using Carnot cycle. Okay. So this is another way of representing the Carnot cycle. Okay. Okay, I'm not going to the detail of what is called the Clausius inequality. Right. But it's a very, very important inequality. I just can tell you that this Clausius inequality, it is talking about a quantity called delta Q by T over a cyclic process. According to Clausius inequality, if you have a cyclic process, arbitrary cyclic process, then this quantity delta Q by T over a cyclic process is always less than or equal to 0. With equality holds for reversible cycle. Okay. This equality holds for reversible cycle. And inequality holds for if the cycle is irreversible cycle. I already mentioned to you the difference between the reversible and irreversible cyclic process in the beginning, right? Right. Suppose I take a cyclic process, A to B along path 1 and B to A along path 2. That process, that cycle is a reversible cycle. For that reversible cycle, this quantity is exactly equal to 0. Suppose I take a path A to B along path 3 and B to A along path 2, that can be thought of as a irreversible cyclic process. For such a process, the quantity on the left hand side is less than 0. That is the meaning of this inequality. Okay. Yeah. So with this inequality, one can define a quantity called ds. As we already know, delta Q is not an exact differential. Okay. But delta Q by T turns out to be an exact differential. Why? Because as I told you earlier, this quantity will be exactly 0 for a reversible cycle, right? So if I apply this, if I can compute this quantity for the reversible cycle, that is A1B to A, which will be integral A to B, along the path 1, and this quantity along the path 2. And this quantity will be equal to 0 according to the Clausius inequality, right? So if that is the case, A to B along the path 1 is equal to A to B along the path 2, which means that this quantity is independent of path. And of course, 1 and 2 are paths which are chosen arbitrarily. And so one can say that this quantity, the integral A to B delta Q by T, is independent of path. If this quantity is independent of path, the differential or the integral, which is integrand, which I call it as ds must be an exact differential. If ds is an exact differential, the quantity s is a thermodynamic variable, and which has a special name. We call it as the entropy. Okay, so right. So S can be thought of as a valid thermodynamic variable. Okay, valid thermodynamic variable, and ds is an exact differential. Okay, so if that is the case, the delta S will be SB minus SA, which is independent of path, right? The change in entropy for any process from A to B depends only on the entropy at the endpoints, right? So in that sense, we say that the second law of thermodynamics gives you a thermodynamic quantity called entropy, while the first law of thermodynamics gives you a thermodynamic variable called U. Is it clear up to this point?
Yes, sir.
Okay. So U and S are extremely important because they are, thermodynamic variables in addition to the quantities like pressure, volume, and temperature. Okay. Right. Okay. Of course, one can discuss various properties of entropy. I am not going to the detail of that. Yeah. One should also remember that for a system in thermal isolation, the change in entropy is either 0 or positive. Okay. That's another way of putting down this second law of thermodynamics, with equality holds for reversible process. Okay. In thermal isolation, the entropy always increases. That you have to keep it in mind. Okay. It's a very, very profound statement. So you always see when you measure any quantity of a system, you always see that the quantity will be either increasing or decreasing, right? But entropy is such a quantity. If you measure the change in entropy of a thermally isolated system, it always increases, right? So is there any quantity which always increases? Can anyone say other than entropy?
Time.
Time, exactly, very good. So time is the only quantity which is always increasing, right? The change in time is always positive. So it is something like time. The change in entropy is something like time. So one can say that this change in entropy is something like a time arrow. Okay. Right. Yeah, one can give simple examples like what happens to the change in entropy when there is a heat conduction from system 1 to system 2. If there is a heat supplied from system 1 to system 2, the change in entropy is always positive. Of course, this is true if the system is in thermal isolation, right? Heat conduction is a very, very important process which happens in the nature, frequently around us, right? And another process is friction, right? If one system, runs over the other system, there is a friction takes place. If this friction takes place at some temperature T, then the change in entropy in this process is also positive. Okay, right. So these are all irreversible processes. Okay, they're all natural process where the entropy is always increasing. Okay, right. So one can talk about irreversible, more properties of irreversible process. So second law also says that in thermal isolation, a process which decreases the entropy is prohibited. And of course, which implies that entropy is maximum at equilibrium. Entropy always increases, but it will reach to the maximum only when the system reaches equilibrium. Okay. Right. No, I don't want to discuss more. There are a lot of things to, time is very short. So to appreciate the second law, I have examples, fresh tomato always gets rotten, right? You never see a rotten tomato becomes a fresh tomato. Similarly, aging is an inevitable process, right? Wear and tear of machinery, diffusion of a drop of ink in water. They are all the process, natural process where entropy always increases. Okay. Okay. Yeah, I would like to conclude this thing before I go into other topics. Now, I already mentioned to you that du is equal to delta Q minus delta W, right? So this is coming from the thermal energy and this is coming from the mechanical energy, right? Now, we are going to generalize the first law by adding in another term, which I call it as delta C. Delta C is actually called as the change in energy due to chemical process. Okay, this is the complete form of the first law of thermodynamics, right? Until now, we have not talked about the chemical energy, right? There's another form of energy called chemical energy, which is added over here. Du is equal to delta Q minus delta W plus delta C. Okay, delta Q, delta W, and delta C, all of them are not exact differential, but this combination is exact differential. That you have to keep it in mind. And so you have three equilibriums like thermal, mechanical, and chemical equilibriums, as I mentioned earlier. Okay. For a gaseous system, as you know, du equal to delta Q. The first term is nothing but TdS, right? I just mentioned that ds is equal to delta Q by T, which means delta Q is equal to TdS, right? And minus PdV. And this term, I write it as mu times dN, mu times dN. What is N here? N represents the number of particles in the system. So if suppose the system exchanges particles in addition to energy, if the system exchanges energy with the environment, that is being taken care by this term. If system exchanges number of particles with the environment, that is being taken care by the third term. So I write the third term as mu times dN, where dN is the change in number of particles of the system. And here there is a factor mu. The mu has a special name, which is called as the chemical potential. So T is the temperature, P is the pressure, and mu is the chemical potential. And this is the final form of the first law of thermodynamics for a gaseous system. Okay, so you have many quantities here: P, V, T, U, S, mu, and N. These are the quantities you come across in the thermodynamics, and the relation among these quantities are the main concern in the thermodynamics. How these quantities are related? Unfortunately, the relation among these quantities are written down only in terms of partial derivatives. Okay, right. As we know, the U comes from first law and S comes from second law, right? So one can also write ds as 1 by T du plus P by T dV minus mu by T Tn. So what it says that, as you see from here, the U depends on S, V, and N, right? The change in U depends on change in S, change in V, and change in N. Similarly, and that sense you say U is a function of S, V, N. And similarly, you can say S is a function of U, V, N, right? Implying that S is a function of U, V, N. And this this S is such that if ds is 0, S is maximum at equilibrium. That I already mentioned to you, right? So with this, I would like to conclude by saying that if ds is exact differential and S is a function of UVN, one can always write ds as dou S by dou U du plus dou S by dou V dV and dou S by dou N dN. Of course, when you take a partial derivative, the other variables will be constant, right? So this expression you can compare with this expression, and you can imply this comparison imply that this term dou S by dou U is equal to 1 by T, dou S by dou V equal to P by T, and dou S by dou N or minus of dou S by dou N equal to mu by T, right? So these are the relations you come across in the thermodynamics. Of course, you come across many such relations, and all the relations you come across are in terms of partial derivatives. Okay. Sometimes it is also this is also taken as a definition of entropy. Definition of temperature, which is used in the subject of statistical mechanics. Yeah. So I think I will stop these slides, and I'll move on to other couple of topics. Other topic, then I will move on to some problems to solve. Are there any questions here up to this point? Any
So please
questions?
ask if you have any questions.
Okay. Once again, I assume that you are following me without difficulty. Okay. So now I move on to a topic called thermodynamic potentials. Okay, quickly, then I will do a few problems. Okay.
Sir, excuse me, your screen is not visible, sir.
Yeah, I'm yet to share. Okay. Is it fine now?
Yes, sir. Fine.
Okay. So until now, I have talked about the first and second law of thermodynamics. If you understand the first and second law of thermodynamics from the point of view of exact differential, you will be able to understand the remaining, thermodynamic relations without much difficulty. I just want to emphasize only the concepts, okay? And you will definitely have a set of problems from the first law, second law, and exact differentials, and so on, and also from the Carnot cycles and things like that, okay? Right. Now I move on to the topic of what is called the thermodynamic potentials, okay? Right. So before introducing to the notion of thermodynamic potentials, I would like to give a little bit input on the necessary mathematics required to appreciate the thermodynamic potentials. So if you understand the thermodynamic potentials, one can understand how these Maxwell's relations comes up. Because I see that, usually in many questions, these Maxwell's relations are being asked. Okay, the questions based on Maxwell's relations are asked. Okay. Okay, so what we need to appreciate, what we need to understand now is what is called the Legendre or contact transformation. So the idea is the following. Suppose you have a function f of y, okay, and you want to transform this function f of y into another function of u. I want to transform f of y into g of u, where y is the old variable and u is the new variable, and the new function is g. Okay. So how do I transform? Where u is actually defined as the df by dy. Okay. Suppose I have a function f of y, which is something like this. Now, u is actually the df by dy at some point. You take some point on this curve, u is actually the slope, right? U is the slope. I take this straight line and this intersection, I call it as G. So naturally, G will be a function of U. As U changes, G also changes. G is the intercept, right? So on this point, since the point is arbitrary, what I argue for one point is true for any point on this curve. So since this point lies on this curve as well as on this straight line, I can write that f of u, f of y is equal to g of u plus u times y. Are you able to appreciate this equation? On this, at this point, f of y is equal to g of u plus u times y. What is on the right hand side? It is nothing but the equation of a straight line. All right. G is the intercept and u is the slope and y is the independent variable. So right hand side, I'm just writing the equation of a straight line, which is equal to f of y at this point. At this point, this equation is true, right? So then I can immediately write down g of u equal to f of y minus u times y, right? So with this, I'm able to transform f of y into g of u. So here u is the new variable and y is the old variable. So the transformation says that f of y minus old variable into new variable gives me the function g of u, where u is the df by dy. So the same idea, by the way, this transformation is called as the Legendre or contact transformation. Okay. This idea can be extended immediately for a function of more than one variable. Okay. Suppose I have a function f of x comma y, which is transformed into g of x comma u. I just write it as g of x comma u equal to f of x comma y minus u times y. U is the new variable and y is the old variable, right? So this transformation is what we are going to use it to introduce the notion of thermodynamic potentials, which are extremely important in very many to understand very many, real processes. Okay. Is it fine up to this point?
Yes, sir.
Okay. Of course, this is the kind of transformation you also come across when you transform from Lagrangian to Hamiltonian in classical mechanics. Okay. Right. We are going to repeatedly use this Legendre transformation here to understand, to introduce the notion of thermodynamic potentials. As I told you earlier, u is a function of s comma v. Of course, it's also a function of n. Now, u is a function of s, v, n in general. Okay. For the time being, I'm just writing u as a function of s comma v. Okay. I assume that there is no change in the number of particles. If u is a function of s comma v, I want to define a new function which is a function of s comma p, where p is a pressure. So what I should do is v is a old variable and p is a new variable. Of course, here I'm going to replace v by minus p. Okay. So v is my old variable and p is my minus p is my new variable. So the way I transform is u of s comma v plus p times v. V is a old variable and minus p is the new variable. So u plus pv is a new function which is called as the enthalpy. So such a function is a function of S and P, is a function of entropy and pressure, right? U is a function of entropy and volume. If I define a new function in this way, that H is a function of S and P, right? So in this way, I can define many number of functions of my choice, right? So H is called as the enthalpy, which is defined as the U plus PV, right? So U is a thermodynamic variable, P is a thermodynamic variable, and V is also a thermodynamic variable. which implies that H is also a thermodynamic variable, which means that if I look at the infinitesimal change in H, dH must be an exact differential. Okay, so I just differentiate this quantity. dH is equal to du plus pdv plus vdp. And we already know from first law that du is equal to TdS minus pdv. And you have this pdv plus vdp. So pdv terms cancels off. So what you have is dH is equal to TdS plus vdp, right? And since dH is an exact differential, this T must be dou H by dou S, right? H is a function of S comma P, right? So dH is dou H by dou S ds plus dou H by dou V, dou H by dou P dP, right? So you can equate T to be this dou H by dou S and V is equal to dou H by dou P. Is it clear? Is the relation clear to you?
Yeah, participants, please respond. If you have any doubts, you can ask.
It's clear, sir. It's clear.
Okay, good. Thank you. So the same thing we are going to follow to define few more functions. I'm going to define another quantity called Helmholtz function, which is u minus ts. So u minus ts, u as I know is a function of s comma v, right? What I'm going to do is I'm going to define a new function which will be a function of v comma t. That means the whole variable is s and the new variable is t. So essentially I just subtract u by subtract ts from u. So u minus ts is defined as f, which is called as the Helmholtz function, which is a function of volume and temperature. Okay. So I repeat the same. df equal to, so since u, ts all are thermodynamic variable, f is also a thermodynamic variable and df is an exact differential, right? df is equal to du minus tds plus sdt. You just expand it. ds is TdS minus PdV minus TdS minus SDT. So these two terms cancels off. So what you have is minus PdV minus SDT. So since dF is an exact differential, this P, right? P must be equal to this. P is equal to minus dou F by dou V and S is equal to minus dou F by dou T. Of course, it's a partial derivative at constant temperature and partial derivative at constant volume, right? So you have more such relations. Relation between, I mean, you write P in terms of F and you write S in terms of F. Okay. As you did earlier for the enthalpy, right? I'm also going to introduce another function called the Gibbs function. You do the same thing. F plus PV is G. So here the whole variable is, V and the new variable is P. Okay, minus P, of course. That's why I have a plus here. So F is actually the Helmholtz function. F plus PV is called as the Gibbs function G, which is a function of P comma T, which is also equal to H minus Ts. You can also transform H to G in this way. H is a function of P and S, as we just saw. So I'm going to replace S by T. H of P comma S minus Ts. Okay, you can repeat the same as we did earlier. Differentiated on either side. dg equal to dh minus tds minus sdt. And dh is, what is dh? dh is tds plus vdp, right? TdS plus VdP minus TdS minus SDT. TdS terms cancels off. what you have is VdP minus SdT, right? Again, dg is an exact differential, and so this quantity, of course, g is a function of p comma t, right? So v must be equal to dou g by dou p at constant t. Similarly, s must be equal to minus of dou g by dou t at constant p. Is it clear to all of you?
Yes, sir.
Okay. So we define set of functions like this, right? H is a function of s comma p, and v is a function, sorry, f is a function of v comma t, and g is a function of p comma t. So one can ask the question, why one needs to introduce more and more functions to make life complicated, right? We already have more quantities. The idea is that if you have functions which are depending on some variables, and if those variables are measurable quantities in the laboratory, then it is easy to handle. For example, g is a function of p comma t. P and t are measurable quantities in the laboratory, and f is a function of v comma t, right? So V and T are measurable quantities in the laboratory, right? In many of the chemical reactions, they are taking place at constant volume and constant temperature and constant pressure and constant temperature. So in many of the chemical processes, these Helmholtz functions and Gibbs functions are extensively used to understand those chemical processes. Okay, of course, most of the natural processes can be thought of as a chemical process, as a matter of fact. Okay, yeah. Now we come to the Maxwell's equations. As I already mentioned, U is a function of S comma V, H is a function of S comma P, and F is a function of V comma T, and G is a function of P comma T, right? All are thermodynamic variables. You can also call them as a state functions, right? I mentioned to you earlier that if you have a function f of x comma y, if it is a state function, and if df is an exact differential, then they should obey this condition, right? They should obey this condition. Dou by dou y of dou f by dou x is equal to dou by dou x of dou f by dou y, right? So if you think of this function, u is f and s and v are like x and y, right? We just put it over here, you will get the first Maxwell's relation, which is this. Dou p by dou v equal to minus dou p by dou s, right? And if you apply this relation for H, where S and P are like X and Y, H is F, S and P are X comma Y, you will get the second Maxwell's relations, which is dou T by dou P equal to dou V by dou S. You don't have to remember this. If you know the definition of these functions, you just have to substitute and get it immediately. Okay. And similarly, if you take F as your function f of v comma t, if you think of like f of x comma y, v and t are your x and y. You just apply this relation, partial derivative relation, you get the third relation, which is dou s by dou v equal to dou p by dou t. Similarly, if you apply this relation for g, the Gibbs function, you get the last relation, dou s by dou p equal to dou v by dou t. Of course, minus is there. So these four relations are called as the Maxwell's relations. If you know these Maxwell's relations, one can do many problems. I see this the questions based on Maxwell's relations are repeatedly occurring in the previous questions. So